Okay, we are into chapter 10, and we're talking about solutions. And we talked about the idea of like dissolves like. So remember, as we talked about, really those intermolecular forces play a large role in a lot of how molecules and molecules interact with each other in terms of whether they're soluble or not. They also play roles, obviously, in things like boiling points and melting points. And what we talked about was that things tend to be soluble in each other if they're using similar types of intermolecular forces. And that basically means that, as we talked about, again, if you got ionic and polar, you're going to be good. They're going to be soluble in each other. Again, they're going to use something like ion dipole interaction. If you got, again, a polar molecule and a polar molecule, they will either use dipole, or they may use hydrogen bonding. And if you have some nonpolar and nonpolar guys together, they also will be soluble in each other, as they will use dispersion forces. And again, as we talked about, pretty much just crossing over there from polar to nonpolar is going to be problematic. So again, nonpolar, polar, not going to really work because they are using very, very different types of interactions. Um, we finished up last time just kind of reviewing some important concentration type units that we're going to see here in the last part of the chapter about colligative properties. Just a couple of reminders. We saw molality, which is little m, moles of solute, kilograms of solvent. Not to be confused again with molarity, which is big M, moles of solute, liters of solution. We also will see a couple other things that we saw before, like mole fraction, which is abbreviated with an X, and that's the moles of what you're interested in divided by the total moles. We'd also talked about our percent mass to mass, which was, again, the mass of the solute divided by the mass of the solution times 100%. So as we talked about last time, we pretty much hit all that stuff when we were doing stoichiometry and titrations and all that kind of stuff. Uh, and again, we definitely will see these guys coming in to play here with our colligative properties. Any questions on any of that stuff from last time? All right, then to pick up where we left off, we're going to talk about colligative properties of solutions. And colligative properties basically means that is really dependent on the number of particles that are present in, say, a solution. The more particles, for example, present in a solution, the more sort of disruption it will cause. So, for example, if you had just regular old, say, water molecules, solvent by itself, and if you wanted this guy to freeze, you remove your energy. And these guys could pretty much kind of come in contact with each other with no sort of situation or problem. And there's really nothing kind of in the way of them except for other water molecules which they could interact with. Now, if you take the same water molecules and you put in some water molecules, and maybe you decide you want to dissolve some sodium chloride in there, some type of ionic compound like a salt. Now you got some ions in there with it. And what happens in this situation is, as it goes to freeze, they kind of get in the way. So it's a little bit harder for them to come together because there's a lot more stuff in the way, is a good way of saying that, I suppose. There's a lot more stuff in the way. It's just going to kind of get in the way of that, just that natural process of the solvent molecule by itself to freeze. In addition, if we were talking about something like boiling, same idea. If this water molecules want to boil, they just got to kind of escape to the surface of the liquid. And if you got these guys that want to boil over here, again, they got a lot of things kind of in their way to try to get out of that solution and sort of leave the solution, say, at the boiling point. So one of the couple things that we will see is, for example, when you put some solute in a solution, it can affect the temperature at which that solution will freeze or boil, and it will freeze or boil at a different temperature than, say, just the solvent by itself, say, just like water by itself. And again, the presence of those particles is really what's sort of causing the problem. So one of the things that it can affect is vapor pressure. So as we talked about earlier, vapor pressure is the pressure of the gas above a liquid. So remember, again, at the surface of a liquid, you got molecules jumping out into the gas phase. You also have ones returning back to the liquid phase. And you will end up with a certain amount of vapor that comes out of the solution, and those are gas molecules above the liquid, and that again is the vapor pressure. Now, the vapor pressure of a substance depends only on the nature of the substance. When you add a solute to a substance, the vapor pressure is lowered because the molecules of the substance cannot evaporate to the surface again as easy as they could if nothing was in the way. So back to my drawing again with a lot of little things sort of in the way. Again, it's going to take longer for these guys to sort of escape. And if it takes longer for these guys to escape, you're going to get less molecules escaping into the gas phase. And because of that, you're going to have less gas over the liquid, and that's going to lower the vapor pressure because you don't have as much gas over the liquid in that case. You could calculate the vapor pressure by Raoult's law here, and that is the pressure of, or the vapor pressure of a solution is equal to the mole fraction times the vapor pressure, basically, of the pure substance by itself or pure solvent by itself. The vapor pressure is lowering, is defined as the vapor pressure of the pure substance minus its vapor pressure in the solution. So once again, the presence of those particles in the solution is going to cause less of them to escape the actual substance, and you'll have a lower vapor pressure. Again, these are pressures, and this is again the mole fraction we were just talking about and have talked about previously in some other chapters. So why don't you take a second here and see if you figure it out. The vapor pressure of ethyl alcohol is 665 torr, 665.5 torr. Calculate the vapor pressure of ethyl alcohol in 0.2 moles of glucose, or when 2.2 moles of glucose is dissolved in the 1.25 moles of the alcohol. So take a moment there and see what you come up with. Okay, so let's take a look. So we're going to use our Raoult's law there to figure it out. So in this particular case, we have our kind of normal vapor pressure of ethyl alcohol, which is 66.5 torr. We want to calculate the vapor pressure, which would be this guy here, of the ethyl alcohol in a solution that is 0.2 moles glucose. So this 0.2 moles of glucose, this is our solute we're adding. This is also sometimes referred to as a non-ionic solute. And that is because glucose is carbons, hydrogens, oxygens held together by some electron sharing. And what that basically means is when you toss glucose in, you get one molecule in the solution per molecule you basically toss in there. So it's a one-to-one. It's not going to fall apart into a bunch of different things, which is really important when you're doing colligative properties since it's all based on how much stuff is floating around that solution. So in this case, you get a one-for-one sort of situation. And we're going to dissolve it in 1.2 moles there of our ethyl alcohol. So we do need to figure out our mole fraction of the ethyl alcohol. So that is going to be the moles of the ethyl alcohol divided by our total moles, which would be 1.25 plus 0.2 moles in this case. And that's going to get us here 1.25 divided by 1.25 plus a 0.2. Going to give us 0.86, we'll call it 21. That's our mole fraction. We have that. So now our vapor pressure of our ethyl alcohol should be our 0.8621, basically 86% of what it normally is, and 66.5 torr, which is our normal vapor pressure. So times that by 66.5, and we end up with 57.3 torr here. This is vapor pressure lowering. So again, the presence of all these glucose molecules floating around in the solution is going to kind of get in the way of those ethyl alcohol molecules being able to escape to the surface as easily. The result of that is you get less of them up here above the solution, and because of that, you see your vapor pressure go down. As you can see, it started there. With that glucose dissolved in there, you end up with 57.3. Any questions on that there? All right. The next sort of property we're going to talk about is freezing point depression. So just like with the vapor pressure, again, having particles in the solution will actually lower the freezing point. So where a solution, not really a solution, but where a solvent would freeze normally, having something dissolved in it will cause the freezing point to go down from where it started. And that is what's known as freezing point depression. Again, the solute particles interfere in that process of everybody coming together. And we do have a formula for that. That is the change in freezing point temperature is equal to Kf times M. This is oftentimes confused by people. This is, again, the change in freezing point temperature. It is not the temperature at which it freezes. So it's just the change between the temperature where the solvent normally would freeze and where that solution is actually freezing. Is that the Kf here is the freezing point constant. And the freezing point constant is a value you look up in a table. And it's really important as well. Sometimes people go to the table and try to look up the freezing point constant and they go, I can't find it. And the reason they can't find it is because they are looking for the freezing point constant of the solution, but the freezing point constant is actually for the solvent only. So that is what you actually would be looking up in that table. So if your solution there is an ionic solution, perhaps your solvent is water, you would look up the freezing point constant for water and not like a sodium chloride solution, which will not be on the table. So it's just the solvent that you look for. The little m here is our friend molality. So that is our moles per kilogram of solvent. Now, because the freezing point is a depression, that means the solution will actually freeze at a lower temperature than the solvent. So it's really important when you do this calculation here and actually calculate the change in the freezing point temperature, you actually take the temperature of the solvent, which will actually be a larger number, minus the temperature of the solution that has something dissolved in it. That's really important because that will give you the correct sign. And what I mean by that is if you kind of do it backwards or do it incorrectly, you'll be adding when you should be subtracting, and you'll be subtracting when you should be adding. So for freezing, because it's the higher temperature as the solvent, you want to go solvent minus solution, and that will get you, again, like I said, sort of the right sign so you don't, like I said, sort of add when you should subtract or subtract when you should add. In addition to freezing point, there's also boiling points affected as well, and boiling point is affected by is elevated. So having something dissolved in a solution will raise the boiling point of the solvent from where it normally is at. So if you had something like water as your solvent, instead of boiling at 100 degrees Celsius, it will boil a little higher than 100 degrees Celsius with what's dissolved in there. Just like in the previous example for our freezing point depression, if your solvent was water, instead of freezing at 0 degrees Celsius, it would freeze at like negative something in terms of its temperature with what is dissolved in there. We have a similar looking formula, and this is the change in the boiling point temperature is the Kb times M. So again, the delta Tb is not the boiling point temperature, but the change in it. Kb is our boiling point constant. Also, much like the freezing point constant, that is for the solvent as well. So it is for the solvent as well. And the little m here is just like the last one. It is our molality, moles per kilogram in this case. And a little bit different than the previous one, which is the change in the boiling point temperature is different in the sense that because the solution is actually going to boil at a higher temperature than the solvent, when we're doing our change in boiling point temperature, we're going to take the temperature of the solution where it boils minus the temperature of the solvent. So for this one, it's opposite. We're going to do solution minus the solvent. Once again, this will allow you to hopefully add when you should be adding and subtract when you should be subtracting. So boiling point elevation, freezing point depression, that is essentially what happens when you put antifreeze in your car, right? Antifreeze does both things, actually. It elevates the boiling point. So if you live in a really hot area, your car doesn't overheat. And if you live in a really cold area, the freezing point depression allows for all the water in your car not to freeze as well. So antifreeze in your car actually does both of those things, raises the boiling point, lowers the freezing point in this case. Let's see here. Here's a table similar to one in your book. The other important thing to remember is sometimes people always get focused on water, which is a lot of times the solvent. If water is not the solvent, you obviously would need to find something else on the list. But in addition to that, we have 0 degrees freezing point for water, 100 degrees Celsius boiling point for water. But if we were doing benzene, it also will have different freezing points and boiling points as well. So those are things you got to keep in mind. So the 0 and the 100 again here specifically for water. And if you're not using that as your solvent, you probably have some different boiling points, melting points, and also obviously some different Kf values. So here you can see for water, 1.86 is the Kf, and the Kb is 0.512 for the boiling point for water. All right. So why don't we try one here? What is the freezing point temperature of 1.7 molal ethylene glycol solution? So why don't you take a moment there and give it a calculation? Okay, so let's take a look at this. So first off, obviously we're doing something with freezing points. So our freezing point equation would be good. Change in freezing point temperature equals our Kf times our molality. Couple of things here. Aqueous ethylene glycol. So aqueous probably implies that it is going to be water as your solvent. So that is what you would want to look up on that chart. Hence, we have our Kf for water. The other thing we know about the freezing point of water, hopefully, that is 0 degrees Celsius is the normal freezing point of water in this case. Ethylene glycol, once again, is a non-ionic or a non-electrolyte, whichever way you like to think about it. Solute that is being dissolved in there, and we basically get one molecule per that goes in, which is important. So in this particular case, they actually just gave us the molality. So most of the time you will have to calculate the molality yourself, but in this case, they gave it to us. So we could actually just put it into our formula here, and this is going to give us 1.86 degrees Celsius times the molality times 1.7 molality here. Those guys are going to cancel, and that is going to give us here 3.162 degrees Celsius. Now, just so we're clear, that is not the answer to the question. That is the change in the freezing point temperature, because that would not be a freezing point depression since water freezes at 0, and now you're trying to say it's going to freeze at 3. That's going the wrong way, right? So this is where that change in freezing point temperature comes into play. Remember here that our solvent's actually going to be a larger value. So we're going to do solvent minus the solution. So this number that we just got is right there. The temperature that the solvent normally freezes at is 0 degrees Celsius minus the temperature of the solution. Bringing this guy that way and bringing that guy that way will give us a temperature at which this guy will freeze not 3.16, but minus 3.162 degrees Celsius. Or we could actually wrap it down a little bit there, 3.2 degrees Celsius negative. And that is a depression from 0 degrees. So again, in this case, by putting some of that ethylene glycol in your engine, it will not freeze the water at 0 degrees. You got to get down to minus 3 degrees for that to kind of freeze. Any questions on that there? So again, that's really important, these relationships here, so that again, you kind of add and subtract correctly and get the right answer. All right, here. All right, so why don't we calculate the molar mass of a compound if 12 grams of it is dissolved in 80 grams of water, and that freezes at minus 1.94 degrees Celsius. Obviously, molar mass is grams per mole. So use the freezing point information there to help you get to the molar mass, and we'll talk about it. Okay, let's take a look. So we're looking for the molar mass, which is grams per mole. So of a compound in a solution, if 12 grams of it is dissolved, so right off the bat, I don't have to figure out that. That is right there. So really here, we're just looking for the moles, and we're going to use really the kind of freezing point information to help us get there. In this case, we have our freezing point formula, our Kf, and times our molality. And in this particular case here, it's dissolved in 80 grams of water, which is our solvent. And we have our freezing point temperature and our Kf value given to us there at 1.86. So that is our freezing point temperature of the solution, which is minus 1.94 degrees Celsius. So once again here, we need to kind of use this formula to get us what we're looking for. A reminder that this here is not the delta TF. That is actually the temperature at which the solution freezes. So the change in the freezing point temperature, again, here is going to be the temperature of our solvent minus the temperature of our solution. We know that the solvent's water, which means the normal freezing point is 0 degrees Celsius. So pop in that number in there, which would be 0 degrees minus a minus 1.94 degrees Celsius. That, by the way, is how the negative sign disappears, basically, in this case. That's going to give us a change in freezing point temperature of 1.94. We now have 1.94 degrees Celsius is equal to our Kf times our molality here. So we can solve for the molality by obviously dividing to the other side here. And that's going to give us 1.94 divided by 1.86, if I hit the numbers right. Still didn't do it. Let's try it one more time here. 1.86. That's going to give us a molality of 1.04. We'll go 3. Remember, molality is moles of solute over kilograms of solvent, and that is what molality is. We are close to what we need. Remember here, we actually just need the moles part. So that is where the mass of my solvent is going to come into play. So since I know I have 80 grams of solvent or water, which is my solvent, I'm going to convert that into kilograms. So there's 1,000 grams in a kilogram. And that's going to tell me I got 0.08 kilograms of solvent. That's going to work good here, so I could get rid of the solvent and be left with moles of my solute. And I'm going to times this by 0.08 kilograms. That's going to cancel out because, again, that's my solvent. And that's going to give me the moles of my solute, which is kind of what I'm looking for. So let's see here. We're going to end up with 0.043 times 0.08, going to give me 0.08344 moles. So at that point, I now have the bottom piece here of what I need. So what's left is we're just going to kind of put both of those numbers in. So the molar mass here should be my grams, which was 12 grams, divided by my moles, 0.08344. And that's going to get me something, hopefully. About 100 and we'll call it 44 grams per mole in this case. Any questions on that? So here we're using basically our freezing point information to figure out the moles. And obviously the grams were given to us so we could figure out the molar mass of our compound. So another sort of application of this colligative property that can help us figure out things like molar mass. Any questions on that one there? All right. That was what we just did. Hopefully I can say it number. Good. All right, so why don't you try this one then? How many grams of ethylene glycol must be added to 1 kilogram of water to give a solution that boils at 105 degrees Celsius? And in case you need these numbers, and oxygen 16. Again, we are talking about boiling in this case. So if we go back to our table here, which we saw earlier, our KB for water 0.512. Yeah, one not too different of a formula, but this is going to be our change of boiling point temperature equals our KB times our molality. Here we have our water, which is our solvent, and we have 1 kilogram of it. And we have the temperature at which it boils the solution, 105 degrees Celsius. And we're looking for the grams of our solute here. So grams of our solute. All right, so we do know that looking at our boiling point temperature, really the one place where solute comes into play is right there at the molality. That is, again, our moles of solute, kilograms of solvent. So we pretty much got to figure out the molality here of the solution so that we can then use obviously the moles of it to get to the grams. So that means we need these two numbers. Once again, here, since water's our solvent, we would go to that table and look up our boiling point constant for water. We would also know that the normal boiling point of water hopefully is 100 degrees Celsius. So again, a reminder that this temperature here is not the same thing as this guy, as that is the change in boiling point temperature. So remember, though, as well, that this is boiling point elevation. which means the solution here is going to be a larger number than the solvent. So we're going to take solution minus solvent here. That would give us the change in boiling point is our 100 and not point 105 without the point 105 degrees Celsius minus our normal boiling point of 100 degrees Celsius, which means this is actually 5 degrees, and again, not 105 degrees. So you want to make sure that you do put the correct temperature in there for the change in either freezing point or boiling point. Again, a very common mistake. People will just kind of roll with that number. That would then give us 5 degrees Celsius is equal to our 0.512 degrees Celsius molality times our molality. Once again, dividing that to the other side is going to give us a molality that is equal to 5 divided by 0.512. Looks like a 9.766 moles per kilogram of solvent. Once again, we know how much solvent we have since it was given to us. It was 1 kilogram. That makes the math pretty easy, I think. That's going to give us 9.766 moles of our solute, which in this case is C2H6O2. Now that I know the moles of it is now just a conversion to grams using the molar mass. So again, if we add up the molar mass there, we got 2 carbons at 12.01 plus 6 hydrogens at 1.008 from the periodic table and a couple of oxygens at 16 each will tell us that we could take our 9.766 moles of C2H6O2. We're going to multiply it by our molar mass, 6207 grams per mole that we calculated from the periodic table. And that is going to get us here 9.766. Looks like maybe 606 grams of our solute there. Yeah. Any questions on that particular one there? So again, you can kind of see that we can use some of this freezing point, boiling point information to figure out some different things along the way. Any questions on that there? All right. Okay, let's see here. Why don't you do this one? Calculate the boiling point of a solution made by dissolving 1 gram of glycerin in 54 grams of water. For our boiling point, so again, we're going to use our boiling point equation. Once again, we're dissolving our solute here, which is non-ionic, and our solvent, which is water. So again, just like in the previous problem there, we would go look up our Kb, 0.512 for water. Also, again, we know our normal boiling point there is going to be 100 degrees Celsius, our boiling point temperature. All right, so in this case, we're looking for the boiling point of the solution. We obviously have the Kb. We do need to calculate our molality in this case. So our molality, again, is moles of solute over kilograms of solvent. So our solvent is 54 grams. Converting that into kilograms here will give us 0.0540 kilograms of water, which is our solvent. For our moles, we have grams and we need moles, so we'll use the molar mass here from the periodic table to do that. So if we add all that together, looks like the molar mass of our C3H8O3 is something like 9209 grams per mole. So taking our 1 gram of it, dividing it by the 9209 grams per mole, going to give us our moles of 0.01086. Now we can calculate our molality here by taking our moles, 0.0186 moles. I feel like I missed a zero in there. I think so. Yep. 0.086. Try that again. 0.01086 divided by our kilograms, 0.0540. Going to give us a molality here of, looks like 0.201. So now we have the molality, and obviously we have the KB, so we can find our change in boiling point temperature as 0.512, which is our constant, times the molality we just calculated. Molality will cancel. That's going to get us here 0.512, looks like 0.103 degrees Celsius. A reminder again that this is not the answer, as that is just the change in the boiling point temperature, not the actual boiling point temperature, because obviously it needs to be elevated from 100 degrees. So the change in boiling point temperature is the temperature of the solution minus the temperature of the solvent. So we have 0.103 degrees Celsius equals the temperature of the solution minus 100 degrees Celsius, which is the normal boiling point of water. We're going to add that to the other side. And by dumping in that glycerin into this solution, we raise the temperature a whopping 0.1 degrees Celsius, basically. So this solution should boil at not 100 degrees Celsius, but 100.1 degrees Celsius in this case. Any questions on that there? Okay. Same one, yeah. All right, so let's take a look. Should hopefully agree. They do, so that's good. All right. The next thing we're going to talk about actually is osmotic pressure and some calculations of osmotic pressure. Osmotic pressure is the pressure that is exerted in a system where you have a semi-permeable membrane, which allows certain size molecules to pass through. Other size molecules cannot pass through. The process of osmosis is where solvent molecules move from a concentration of lower concentration to higher concentration. Higher concentration. So the process of osmosis is molecules will basically move in the way to kind of dilute down the higher concentrated side of the membrane. And that's what creates osmotic pressure. So, for example, if I had salt water on this side of the membrane and I had just pure water on the other side of the membrane, the salt water is more concentrated because it's salt water, so it's got stuff dissolved in it. So by osmosis, the water molecules will flow to the other side here in an effort to dilute down that side. And they'll continue to flow until the slide changes, or until the atmospheric pressure pushing down on it will stop the flow of additional, basically, water molecules. And that is what's known as osmotic pressure. I will stop that flow of molecules coming across that membrane. You could calculate the osmotic pressure with this fun looking equation here. Pi is equal to nRT over V. Remember, N over V is moles per liter, which gives you molarity times RT. And again, the molarity is coming from here. Because ultimately, even though it likes to use all these funky formulas, this is still our favorite formula ever. P equals nRT is basically this formula. So that is basically the same formula, just with some funky symbols going on there. So that's the osmotic pressure, which is basically the pressure And as we did in a couple examples where you're in gas, N over V, moles per liter gives you the molarity. So if you want to just keep remembering the ideal gas law, pretty much you can use it for osmotic pressure. And when you solve for P in this case, again, it's osmotic pressure. This also means, obviously, since it really is the ideal gas law, like normal when you use the ideal gas law here, you do need to have everybody in the right units for everything to cancel out. So again, atmospheres for our pressure, liters for our volume, N is moles, R is our gas constant that we use with that, and T in Kelvin here, so that everything cancels out correctly. So that is our osmotic pressure, and that is the molarity times the gas constant times the temperature in Kelvin. So when we try to use that there, what is the molar mass of a protein? If 5.87 milligrams per 10 milliliters gives an osmotic pressure of 2.54 torr at 25 degrees Celsius. So this should be like a throwback question here from gas laws. Molar mass, which again, ultimately we got to get to grams per mole. So we read through here, we have a protein that is 5.87 milligrams there, I believe. Yeah. So essentially that is the grams part. We do need to convert it obviously to grams, but that would get us there. So really again here for the molar mass, we're just short some moles. I got osmotic pressure. So once again, if you want to use the fancy symbols, you can. I'm just going to roll with the ideal gas law there. And I have an osmotic pressure of 2.45 torr. I have a temperature that's 25 degrees Celsius. Since this is the ideal gas law, I always have R available to me, even though, like usual, never given in the problem. And I do have a volume here of 10 milliliters. So if I take a look here, I got pressure, I got volume, I got R, I got T. There is my missing N that I'm going to need here. So we're going to use our ideal gas law here to solve for moles. Once again, we do need to do some conversions to get everybody into the right units. So we'll go with our pressure first here, 2.54 torr. There is 760 torr in an atmosphere. And that will get us here 2.45 divided by 760. Looks like 0.00322, I'll call it 4 atmospheres. Take it to a few digits. Temperature, like anything else, we'll add a 273 to it to give us a 298 Kelvin. And once again, our volume here does need to be in liters. So we're going to go 10 milliliters. 1,000 milliliters is a liter. Going to get us 0.010 liters. Now we should have everybody in the right units. We're going to solve for N. N is equal to PV over RT, basically taking these guys to the other side. Yeah. Putting in our numbers, we're going to end up with 0.003224 atmospheres, 0.01 liters divided by 0.08206 liters atmosphere Kelvin mole, and our 298 here. Everything's going to cancel out but the moles, and we will end up with too many zeros to write. So let's go with 1.318 times 10 to the minus 6 moles. That is the bottom part that we need. So we're just going to convert our milligrams there into grams first. And there is 1,000 milligrams in a gram. And that's going to move us over as well. 0.87 divided by 1,000. 0.00587 grams. We'll take our moles of 1.318 times 10 to the minus 6 moles. And we're going to end up with a molar mass of something, hopefully. We'll go with 4.45 times 10 to the 3 grams per mole. So that's a pretty big molar mass there for our protein, which is probably fairly big as well. Any questions on that? Pretty much the same calculation we did in the gas chapter to figure out the molar mass of a gas, basically, kind of the same calculation. Well, it's identical, basically, yeah. Any questions on that one there? All right, we're going to lay it up there for